The universe we see is a magnificent lie. Most of its mass is completely invisible, a ghostly substance called dark matter holding galaxies together. Astronomers have faced a cosmic cartography challenge for decades, tasked with mapping a shadow. This video will show you exactly how they traced the invisible web of dark matter, revealing the true architecture of everything. You will learn how they used warped light, ancient echoes, and entire simulated universes to chart what cannot be seen. How do you map a force that hides in plain sight? And what does its hidden structure tell us about our own place in the cosmos? Those stars on the outer arms of spiral galaxies were the first to tell a secret. They moved at speeds that should have been impossible, racing around their galactic centers so fast that the known laws of physics predicted they should have been flung out into the void long ago. The gravity from all the visible stars and gas simply wasn't strong enough to hold them in. It was as if the entire galaxy was wrapped in an invisible, massive hand, gripping those distant stars and keeping them from flying free. Astronomer Vera Rubin and her colleagues provided the most compelling evidence for this in the 1970s, meticulously measuring the rotation of galaxies and finding this same baffling pattern everywhere they looked. The universe, it seemed, was built with hidden scaffolding. This was the cosmic conundrum that forced science to admit a profound truth: most of what shapes the cosmos does not shine. We call this invisible player dark matter. It is defined by what it is not. It does not glow like a star. It does not blaze in the heart of a quasar. It does not even cast a shadow by blocking light. It is utterly dark to every telescope we have, yet its gravitational signature is unmistakable, a ghostly pull that sculpts the universe on the grandest scales. Cosmologists believe it must be a completely new, exotic form of particle, one that rarely, if ever, interacts with the ordinary matter that makes up you, me, and every planet. It simply passes through everything, a cosmic phantom. But if we cannot see it, hear it, or touch it, how could we possibly hope to draw its map? The quest to chart this invisible architecture began with a single, brilliant realization. We may not see the dark matter itself, but we can see what it does to the one thing it cannot hide from, the very fabric of space and time. That missing mass warps the very stage on which light performs. It bends the paths of light rays traveling across the cosmos, creating a natural illusion so powerful it became our first real tool for cosmic cartography. This is the phenomenon of gravitational lensing, and it works because of a prediction from Einstein's theory of general relativity. Massive objects do not just sit in space, they dent the fabric of space-time itself. Think of placing a heavy bowling ball in the center of a stretched rubber sheet. Any smaller marble rolled across that sheet will have its path curved by the indentation. In the cosmos, a massive galaxy cluster acts like that bowling ball, and the light from galaxies far behind it are the marbles. Their light, traveling for billions of years to reach us, gets bent around this cosmic dent. From our viewpoint, the images of those background galaxies are stretched, magnified, and distorted. It is a perfect cosmic magnifying glass, and crucially, it magnifies all mass, visible and dark. By meticulously measuring how much the light is bent, astronomers can literally weigh the cluster, revealing the total amount of matter present. The pioneer of this idea was the brilliant and often overlooked astronomer Fritz Zwicky. Back in the 1930s, while studying the Coma cluster of galaxies, he noticed the individual galaxies were moving far too quickly for the cluster to hold itself together with just the stars he could see. He famously proposed that there must be some form of Dunkel Materie, dark matter, providing the extra gravity. He even suggested this invisible mass could act as a gravitational lens, bending light. It was a visionary leap decades ahead of its time, Today, we see his prediction manifested in two spectacular ways. The first is strong gravitational lensing. When the alignment between a massive foreground cluster and a distant galaxy is nearly perfect, the effect is breathtaking. The background galaxy's light is smeared into long, luminous arcs that curve around the cluster's center. In the most precise alignments, the light forms a complete circle known as an Einstein ring, a halo of distorted starlight. These are the dramatic, unmistakable signatures of immense mass. But strong lensing is relatively rare, requiring that perfect cosmic alignment. To map the broader, subtler distribution of dark matter across the universe, astronomers rely on weak gravitational lensing. Here, the distortions are not dramatic arcs, but tiny, systematic shears. Imagine looking at a field of thousands of distant galaxies. Without any lensing, their shapes would be randomly oriented. But if a vast, diffuse cloud of dark matter lies between them and us, its collective gravity will very slightly stretch each galaxy's image, making them all appear just a bit more elongated in a preferred direction, like a subtle cosmic breeze bending a field of grass. No single distortion is convincing, but by analyzing the shapes of millions of galaxies with powerful supercomputers, a statistical signal emerges. This vast data crunching allows scientists to reconstruct a detailed map of where the mass, including the invisible dark matter, is concentrated. It is like listening to a faint whisper from the void and using it to draw a picture of the speaker. These first maps, painted with the bent light of ancient galaxies, revealed a shocking truth. The dark matter is not smoothly spread out. It forms an intricate cosmic web, a vast scaffolding of dense filaments and massive halos, with the glittering galaxies we see merely clinging to the densest knots like dew on a spider's web. But to truly understand the origin of this vast, invisible web, we must journey back to the very beginning, to a time before stars or galaxies even existed. We must look at the oldest light in the universe, a fossilized echo from its fiery birth. This is the cosmic microwave background. It is the afterglow of the Big Bang itself, a snapshot of the cosmos when it was just 380,000 years old, a time when the entire universe was a hot, dense fog of particles and light. When this primordial fog finally cleared and light could travel freely for the first time, that light began a journey across an expanding universe, cooling and stretching over billions of years until it reached us today as a faint, cold whisper of microwave radiation. It is the most ancient picture we will ever have, and within its seemingly uniform glow, scientists have discovered minute temperature fluctuations, tiny patches that are ever so slightly warmer or cooler than the average. These are not random imperfections. They are the cosmic seeds from which everything, including the dark matter web, would eventually grow. Think of it like the surface of a pond on the first truly cold night of winter. As the water freezes, it captures and preserves every single ripple and dimple from the stones thrown in earlier. The frozen surface tells you exactly where those stones landed and how much energy they carried. The cosmic microwave background is that frozen surface for the entire universe. Its temperature ripples are the imprints of the earliest gravitational tugs, the places where dark matter, even in that infant universe, was already beginning to clump together under its own gravity, creating slight denser patches in the primordial plasma. Space missions like WMAP and later, the incredibly precise Planck satellite, have spent years meticulously charting this radiation, creating a full sky map of these ancient temperature differences. By analyzing the precise patterns of these ripples, cosmologists can perform a kind of cosmic accounting. The size and distribution of the hot and cold spots tell them how much total matter exists in the universe, and crucially, how much of it is the invisible, gravitating kind. The data is unequivocal. Ordinary matter, the atoms that build planets and people, makes up less than 5% of the cosmic budget. dark matter constitutes over 25%. This ancient light confirms that dark matter was the primary gravitational architect from the very start. Its subtle clumps in the early universe acted as gravitational wells, attracting the ordinary matter that would later form stars and galaxies. The pattern etched into that afterglow was the blueprint, the initial set of instructions that dictated where the great filaments and halos of the cosmic web would eventually form. Everything we see in the large-scale structure of the universe today, the glittering galaxies and the vast voids between them, was written in code upon that first light. The ancient blueprint was there in the light, but the actual construction project took billions of years. To witness that epic growth, we needed a universe we could control. If we cannot watch the real web form over eons, perhaps we can grow our own from first principles. This is where science steps from the telescope into the realm of pure computation, building entire universes inside silicon brains. Cosmological simulations like the famed Millennium Run or the more recent IllustrisTNG project are not just animations, they are rigorous experiments. Teams of astrophysicists program the fundamental laws of physics, as we understand them, into some of the world's most powerful supercomputers. They begin with a virtual box representing a vast chunk of the early cosmos, seeding it with a precise recipe based on the cosmic microwave background, a soup of dark matter particles and a sprinkling of ordinary matter. Then they press start. The simulation calculates the gravitational dance of trillions of individual particles over the equivalent of 13.8 billion years. It is a cosmic clock ticking forward millions of years with every second of processing time. What emerges from this digital genesis is nothing short of breathtaking. As the virtual eons fly by, gravity works its magic. The dark matter, responding only to this force, begins to clump and collapse, forming an intricate, three-dimensional spiderweb of filaments. At the intersections of these filaments, massive dark matter halos condense like droplets on a complex network of cosmic wires. Then, within those halos, the simulation introduces the complex physics of gas, stars, and black holes. The ordinary matter follows the gravitational roadmap laid down by the dark matter, flowing along the filaments to collect in the halos where it cools, condenses, and ignites into virtual galaxies. The resulting visualizations are stunning cosmic art, but they are far more than that. They are a specific prediction. This is what the invisible architecture of our universe should look like, according to our best theories. For astronomers, these digital universes are the ultimate testing ground. They can take the maps generated from weak gravitational lensing surveys, the real observational data of distorted galaxies, and hold them up against the simulated maps of dark matter from projects like IllustrisTNG. Do the real filaments match the predicted ones in size and distribution? Do the halos have the same mass and abundance? It is a constant process of compare and refine. When the simulation and reality disagree, it is not a failure, it is a discovery. It means our understanding of the rules, perhaps how dark matter behaves on small scales or how galaxies interact with their halos, needs adjustment. We tweak the cosmic recipe in the code and run the simulation again, evolving our digital universe closer to the one we actually inhabit. These silicon cosmos have become indispensable, allowing us to rewind and fast-forward through time to test ideas we could never observe directly, like what happens when two dark matter halos collide, or how the very first galaxies were born within these invisible cages. The digital universes gave us a prediction, but to confirm it we needed a map of the real cosmos on an unimaginable scale. This meant turning from simulation to survey, from predicting the web to actually walking its luminous strands. We needed to chart the galaxies themselves, for while dark matter is invisible, the cities of stars that form within its gravitational wells shine brilliantly across the cosmos. This became the work of cosmic cartography, and its most ambitious project began with a humble telescope in New Mexico. The Sloan Digital Sky Survey did not just look at the sky, it systematically dissected it. For over 2 decades, this project and others like it have used specialized instruments to capture not just images, but the precise light signatures of everything in their view. They have meticulously catalogued the positions, colors, and most importantly, the redshifts of millions of galaxies. Think of each galaxy in this vast catalog as a bright, luminous pin stuck into a 3-dimensional map of the universe. But what exactly does a redshift tell us, and why is it the key to depth in this cosmic map? When light travels across an expanding universe, its waves are stretched, much like the sound of a siren dropping in pitch as it moves away from you. This stretching shifts the light toward the red end of the spectrum. The farther a galaxy is from us, the faster the space between us expands, and the more its light is redshifted. By measuring this redshift with exquisite precision, astronomers can calculate not just how far away a galaxy is, but also how long its light has been traveling to reach us. This turns a flat picture of the sky into a deep, 3-dimensional atlas of cosmic history. With millions of these galactic pins placed in their true positions in space, a pattern emerges that is far from random. When scientists apply statistical tools to this vast dataset, analyzing how the galaxies cluster and group, the hidden architecture begins to materialize. The galaxies are not scattered like confetti. They are strung along vast, invisible filaments, gathering in dense knots at the intersections and leaving enormous, empty voids in between. This is the cosmic web revealed in the light of its luminous inhabitants. Each brilliant galaxy acts as a tracer, a marker that tells us, here, at this point in space, the gravitational pull of dark matter was strong enough to gather the ordinary matter and forge stars. By mapping the luminous tracers with such incredible detail, the surveys effectively trace the outline of the shadow. They show us where the dark matter scaffolding must be, because that is where the galaxies have chosen to build. The Sloan map is perhaps the most famous visualization of this, a slice of the universe showing a delicate, frothy structure of galaxies, a single cross-section of the grand web. This empirical map, built from light collected photon by photon, matched the predictions of the supercomputer simulations with stunning fidelity. We had not just theorized the invisible web, we had seen its outline drawn in starlight. Yet the most dramatic proof did not come from a simulation or a statistical map, but from a single, violent event frozen in the sky. Sometimes the universe stages a perfect experiment, a cosmic crash so immense it reveals the fundamental nature of reality. This is the story of the Bullet Cluster, a place where 2 families of galaxies, each containing hundreds of members, collided head-on at unimaginable speeds. The aftermath of this billion-year-long collision gave us a snapshot so clear it became a smoking gun for dark matter. To understand what happened, picture the components of a galaxy cluster. First, there are the galaxies themselves, those glittering cities of stars which are mostly empty space. Then there is the intracluster medium, a superheated soup of normal matter, gas so incredibly hot it glows not in visible light but in powerful X-rays. And finally, permeating it all, the vast, invisible halo of dark matter that holds the entire structure together. When these 2 colossal clusters rushed toward each other, their different components behaved in utterly different ways. The galaxies, being mostly void, passed through one another like 2 swarms of bees, their stars so far apart that collisions were vanishingly rare. The hot gas clouds, however, were a different story. This normal matter interacts, it creates friction. As the 2 clouds of superheated plasma smashed together, they piled up and slowed down dramatically, like 2 clouds of smoke merging and churning in the wind. This left a huge mass of searing hot gas stuck in the middle of the collision site. But where was the majority of the mass, the gravitational glue of the clusters? Astronomers turned their most powerful eyes to the scene. X-ray telescopes like Chandra saw the brilliant, tangled knot of hot gas sitting between the two swarms of galaxies. But when they mapped the cluster's total mass using the gravitational lensing of background galaxies, they found something astonishing. The peak of the mass, the place where gravity was strongest, was not with the glowing gas in the center. It was with the galaxies that had sailed right through, the dark matter halos which feel only gravity and not the friction that slowed the normal gas, had simply passed through each other unimpeded. The result was a stunning cosmic separation. In one place you had the visible hot gas detected by its X-rays. In another, you had the bulk of the mass revealed only by its gravity anchored to the galaxies. This was not a subtle statistical signal. It was a direct visual separation of what we see from what exerts the pull. As one researcher famously put it, this observation was a direct empirical proof of the existence of dark matter. It showed conclusively that the missing mass was not some strange property of modified gravity. It was a real substance that could be physically separated from normal matter. The bullet cluster proved that dark matter is not a mathematical fix. It is a tangible component of the cosmos that interacts with the universe in its own unique, ghostly way. It sailed through the most violent collision we can observe, carrying the true weight of the universe with it, and leaving the visible matter behind. But mapping a single cosmic collision, no matter how perfect, is not enough. To truly chart the invisible architecture, we needed to move from these singular, dramatic events to a systematic survey of the entire sky, measuring distortions so subtle they had long been considered impossible to detect. This is the monumental task of weak gravitational lensing surveys, where the goal is not to find dramatic arcs, but to measure a whisper of a warp across billions of galaxies. Imagine looking through a vast, slightly imperfect windowpane at a field of 1,000,000 distant lights. Each tiny bulb appears just a little stretched, not into obvious smears but into subtle ellipses. If the warping of the glass is smooth and coherent, you could, in theory, analyze the collective pattern of all those stretched lights to reconstruct the exact contours of the flaw in the glass. Now replace the windowpane with the entire gravitational field of the cosmos, and the distant lights with billions of faraway galaxies. That is the essence of these surveys. Projects like the Dark Energy Survey, which spent 6 years scanning 1/8 of the southern sky, do not hunt for rare, perfect alignments. Instead, they meticulously catalog the shapes of hundreds of millions of galaxies, searching for that coherent statistical signal, the faint imprint left on their light as it passed through the diffuse filaments and halos of the cosmic dark matter web. The technical challenge here is almost incomprehensible. The lensing signal they seek is incredibly small, typically distorting a galaxy's shape by less than 1%. To isolate that cosmic whisper, astronomers must first account for a cacophony of other distortions. The Earth's atmosphere blurs the starlight, a constant shimmer that must be mathematically corrected. The telescope's own optics and sensors introduce minute imperfections, and perhaps most fundamentally, galaxies are not perfect, round dots to begin with. They have their own intrinsic, random shapes from spirals to ellipticals. Separating the true gravitational shear from this natural variation is an exercise in statistics on a galactic scale. It requires measuring so many galaxies that the random intrinsic shapes average out, leaving only the coherent distortion imprinted by the dark matter. The upcoming Vera Rubin Observatory's legacy survey of space and time will take this to a staggering new level. Over a decade, it will image the entire southern sky every few nights, creating the deepest, widest astronomical movie ever made. It will measure the shapes and positions of over 20 billion galaxies. The data set will be so vast that scientists can slice it into cosmic time layers, creating not just a map, but a three-dimensional mass map of the universe's history. They will see how the dark matter web evolved, how filaments thickened and halos merged over billions of years. The payoff from this painstaking work is a direct, empirical picture of the distribution of all mass, the ultimate map of the invisible. It reveals the cosmic web not as a theoretical prediction or a tracing of luminous galaxies, but as a gravitational landscape measured in its own right, a silent topography shaping everything we see. The faintest echo from the dawn of time is written into the spacing of galaxies. As we chart the luminous traces of the cosmic web, we find more than just a random scattering. We uncover a subtle, rhythmic pattern. Billions of years ago, when the universe was a seething, opaque plasma, it was filled with sound. Not sound as we hear it, but colossal pressure waves rippling through the hot soup of particles and light. These were Baryon acoustic oscillations, and their story begins in the first moments after the Big Bang. In that unimaginably dense and hot state, dark matter was already beginning to clump under gravity, creating slight gravitational wells. Ordinary matter, however, was a different story. It was tightly coupled to light, forming a single, viscous fluid. Where dark matter pulled, this ordinary matter would try to fall inward, but the intense pressure of the trapped photons would push it back out, creating a spherical sound wave that propagated outward from every dense seed. This cosmic tug-of-war between gravity and radiation pressure created ripples like a stone dropped in a pond, but on a scale encompassing the entire observable universe. Then, at the moment of recombination, when the cosmic microwave background was released, the music suddenly stopped. The universe became transparent, the ordinary matter and light decoupled, and those pressure waves froze in place, fossilized. They left a permanent imprint, a preferred scale where matter was slightly more likely to be found. The radius of that frozen wave, the distance it traveled before the music stopped, is about 500 million light-years. This is our cosmic standard ruler. Think of it like finding a vast, invisible grid etched across the cosmos, with a repeating unit of 500 million light-years. When astronomers analyze the three-dimensional maps from surveys like the Sloan Digital Sky Survey, they do not just look for where galaxies are. They search for this specific scale in their clustering. By measuring how this 500 million light-year signature appears stretched or compressed at different distances, and thus at different epochs in cosmic history, they achieve something remarkable. They can measure how the universe itself has expanded over time with extraordinary precision. It is as if we had placed a ruler at the beginning of the universe and can now see how its markings have been stretched by 13.8 billion years of cosmic growth. This provides a direct geometric test of the expansion history, independent of supernova or other methods. More importantly for our map of the invisible, it traces the growth of the entire matter distribution, the scaffolding laid down by dark matter. By seeing how the clustering of galaxies, which follows the dark matter blueprint, evolves and how this standard ruler changes, astronomers can measure the gravitational tug of the entire cosmic web. This offers a crucial test for the nature of dark energy, the mysterious force accelerating expansion, and for the laws of gravity themselves on the largest scales. Does the growth of structure match what we expect from Einstein's theory within a universe dominated by dark energy? The frozen sound waves from the infant cosmos have become one of our most powerful tools for auditing the universe, weighing its contents, and confirming the invisible architecture that guides everything. The frozen sound waves gave us a cosmic ruler, but to measure it we must first process a deluge of data so vast it defies human comprehension. Modern telescopes are no longer simple cameras, they are fire hoses of information, generating petabytes of raw images every single night. Within this digital ocean of starlight, the subtle signals of dark matter are buried under layers of cosmic noise, atmospheric blur, and the random shapes of billions of galaxies. Finding the true architecture of the invisible web in this chaos is a task that has pushed astronomy into a new frontier, one defined not by glass lenses but by silicon chips and neural networks. This is where the story of mapping dark matter converges with the revolution in artificial intelligence. To navigate this data deluge, scientists are turning to a powerful new partner: machine learning. These are not sentient machines, but sophisticated algorithms designed to recognize patterns. The process begins in the simulated universes grown inside supercomputers. Researchers feed these algorithms millions of training examples, showing them both the raw, mock telescope images and the ground truth, the complete map of dark matter that the simulation knows is there. It is like showing a student countless examples of a hidden object in a complex picture, until they learn to spot its shadow no matter how well it is camouflaged. The algorithm learns to associate specific, nearly imperceptible distortions in galaxy shapes with the underlying presence of a dark matter filament, or to identify the gravitational signature of a diffuse halo. Once trained, this digital assistant can then be unleashed on the real observational data. It scans through petabytes of telescope images from surveys like the Dark Energy Survey with a speed and consistency no human team could ever match, flagging potential weak lensing signals and reconstructing mass maps with unprecedented precision. The result is an acceleration of discovery that is changing the field. What once took months of painstaking statistical analysis by large collaborations can now be refined and cross-checked in a fraction of the time. But the true promise of these tools goes beyond mere speed. Machine learning excels at finding patterns we did not specifically tell it to look for. By analyzing the maps it helps create, these algorithms might one day point to anomalies, strange overdensities or peculiar geometries in the dark matter web that defy our current simulations. Could it highlight the ghostly imprint of a long-ago collision between dark matter halos, or even hint at subtle interactions between dark matter particles themselves, a possibility that has eluded direct detection for decades? This partnership between human intuition and artificial perception is crafting the most detailed charts of the invisible cosmos we have ever possessed, turning raw data into a legible story of the shadow universe. Yet even the most detailed map leaves a fundamental question unanswered. What is the ink itself, the substance that traces these cosmic filaments and halos across the void? Our charts reveal the architecture, but we have yet to identify the architect's material. The quest to understand dark matter's nature has led physicists down two very different but equally compelling theoretical paths. The first candidate emerged from a beautiful symmetry in particle physics. For decades, the leading idea has been the WIMP, the weakly interacting massive particle. Its name describes its essence perfectly. It would be massive, perhaps dozens or hundreds of times heavier than a proton, and it would interact with ordinary matter only through the weak nuclear force and gravity. This profound weakness is why it passes through planets and people as if they were not there. The theoretical appeal of WIMP is deeply elegant. They are a natural prediction of a framework called supersymmetry, which proposes that every known particle has a heavier, supersymmetric partner. The lightest of these superpartners could be stable and, crucially, would have been produced in copious amounts in the hot, early universe. Calculations show that the relic abundance of such particles left over from the Big Bang would automatically match the amount of dark matter we observe today. It is a stunning coincidence that physicists call the WIMP miracle, a hint that nature might favor this elegant solution. For years, this made WIMP the undisputed front-runner, guiding the design of massive underground experiments. These detectors, buried deep in mines and mountains to shield them from cosmic rays, wait patiently for the once-in-a-universe event, a WIMP from the galactic halo bumping into the nucleus of an atom in a vat of ultra-pure xenon. They listen for a whisper of energy, a signature of the invisible world making fleeting contact with our own. But so far, the silence from these exquisite experiments has been profound. Not a single confirmed collision has been recorded, pushing the possible mass and interaction strength of WIMP into ever more constrained corners. This growing silence has given renewed energy to a different and far more ghostly candidate, the Axion. Where the WIMP is a heavyweight, the Axion is a featherweight, potentially billions of times lighter than an electron. It was not invented to solve the dark matter problem, but to fix a deep puzzle in the theory of the strong nuclear force, known as the strong CP problem. In simple terms, the equations allow for a symmetry that should be broken, yet our measurements show it is perfectly preserved. The Axion is a hypothetical particle that glides into the equations and elegantly restores this balance, a theoretical necessity that, as a bonus, could also be dark matter. Because Axions would be so incredibly light, they would behave more like a pervasive cosmic field than discrete particles. Billions could be passing through your hand every second. Their detection requires not massive vats of liquid, but incredibly sensitive magnetic fields and microwave cavities, devices that try to coax these shy particles into revealing themselves by converting into photons under the right conditions. The choice between these candidates is not just academic, it changes the story of our cosmic map. A universe built from heavy WIMP would form structure in a top-down manner, with large halos forming first and then fragmenting. A universe of ultra-light Axions, behaving as a coherent wave on cosmic scales, might suppress the formation of the very smallest galaxies, leaving a distinct fingerprint on the fine-scale structure of the web. The maps from the Vera Rubin Observatory will scrutinize these tiny dwarf galaxies, searching for that missing population, a clue written in the voids of the cosmic ledger. The journey from the vast filaments of the cosmic web to the silent depths of an underground lab is a single, connected pursuit. We are tracing the shadow not just across space, but deep into the heart of matter itself. Even the most detailed map can be contested, for a chart is only as good as the theory used to draw it. The stunning success of the dark matter paradigm in explaining the large-scale cosmos does not silence all questions, and a small but persistent group of physicists have pursued a radically different path. What if the problem is not missing matter, but missing physics? Their proposal is known as modified Newtonian dynamics, or MOND. Instead of filling the universe with an invisible substance, this theory suggests we simply do not yet fully understand gravity itself, especially in the extremely weak field regimes found in the outer reaches of galaxies. The idea is elegantly simple, and on certain scales it is surprisingly effective. In the vast, sparse outskirts of spiral galaxies, where stars feel only a whisper of gravitational pull, MOND proposes a subtle tweak to Newton's laws. This modification can accurately predict the observed rotation curves of many galaxies without needing a single particle of dark matter. It is a compelling thought that the mystery might be solved not by discovering something new, but by refining our grasp of the oldest force. Yet for all its elegance on the galactic scale, MOND faces profound challenges when confronted with the full breadth of cosmic evidence. It struggles to explain the clean separation of mass from visible gas witnessed in the bullet cluster, a phenomenon that dark matter handles with ease. More critically, the intricate pattern of hot and cold spots in the cosmic microwave background, the very blueprint of the early universe, is exquisitely tuned by the presence of dark matter. Reproducing that precise pattern with modified gravity alone has proven extraordinarily difficult. The debate between these frameworks is not a weakness of cosmology, but a sign of its health, a rigorous stress test for our understanding of reality. This scientific tension extends into other puzzling corners of the map. Take the missing satellites problem. Our most sophisticated simulations of cosmic structure formation predict that our Milky Way galaxy should be surrounded by hundreds, even thousands, of small dark matter clumps, each potentially hosting a faint dwarf galaxy. Our telescopes, however, have found only a few dozen. Where are all the missing satellites? Perhaps our simulations overestimate small-scale clumping, or maybe the process of star formation in these tiny halos is so inefficient that most remain dark and invisible. A related puzzle is the core cusp controversy. Simulations suggest that dark matter halos, especially in dwarf galaxies, should have density profiles that peak sharply at their centers like a steep cusp. Yet observations of how stars move within some dwarf galaxies suggest a gentler, more constant core of dark matter at their hearts. Do these discrepancies point to a flaw in our simulations, a misunderstanding of complex astrophysical processes, or could they be the first hint that dark matter particles have properties, like the ability to interact with themselves, that we have not yet accounted for? These are not failures but frontiers. Every mismatch between prediction and observation is a flashing signpost, urging scientists to look closer, think deeper, and refine the map. The journey to understand the invisible web is a living process, a constant conversation between theory and data, where even the most beautiful chart is always subject to revision. The final map of the invisible is a masterpiece of cosmic art. After the supercomputers finish their calculations and the algorithms sift the data, what remains is not a spreadsheet but a vision, a three-dimensional tapestry of shadow and light that reveals the universe's true architecture. Scientific visualization experts take the raw numbers, the positions and densities of trillions of simulated dark matter particles, and begin a process of translation. They assign color and luminance to density, turning the deepest gravitational wells into brilliant golden knots, and the faintest filaments into delicate strands of blue and violet. The result is the iconic image of the cosmic web, a structure of breathtaking complexity and beauty that looks like a neural network drawn across the void, or the luminous mycelium of a fungus on a galactic scale. These are not artists' impressions in the traditional sense. They are direct visualizations of data, a new form of landscape painting where the terrain is made of gravity itself. For the public, these renderings are a gateway, transforming an abstract concept into an intuitive, almost visceral understanding of a hidden reality. They make the invisible not just comprehensible but beautiful. Yet for the researchers who create them, these tools are far more than communication aids. They are instruments of discovery. The human visual system is exquisitely tuned to recognize patterns, connections, and anomalies. By immersing themselves in a three-dimensional visualization of their simulated universe, scientists can fly through the cosmic web, navigating along filaments and circling halos in a way that static graphs and statistics cannot provide. They might spot a peculiar alignment of several small halos along a faint filament, suggesting a specific merger history, or notice an unusually diffuse region that challenges their models of how structure forms. It is a form of scientific exploration as old as astronomy itself, the act of looking at the sky and seeing a story, but now the sky is one we built from equations and evidence. Visualization expert Dr. Donna Cox, who leads advanced visualization efforts for cosmological simulations, often describes this work as creating a telescope for the simulated data. The visualization software allows researchers to ask new questions, to see relationships in the data they had not thought to query. It turns the abstract map into an explorable world, and in that world, the next great mystery of the dark universe might be waiting, not as a number in a column, but as a strange shape in the shadows, a detail in the tapestry that asks for a closer look. These golden knots in the cosmic web are not just decorations, they are the engines of creation. Each one is a dark matter halo, a vast, roughly spherical cloud of invisible particles held together by its own gravity. Think of the cosmic web as a network of rivers, the dark matter filaments. Where those rivers meet, they form deep lakes, gravitational basins where matter collects. These are the halos, and they are the true seats of power in the universe. Without them, galaxies would never have formed. The story of every galaxy, from our own Milky Way to the most distant smudge of light, begins within the embrace of one of these invisible spheres. Their properties, their masses, and their intricate histories are written into the very structure of the luminous universe we see. To understand galaxies, we must first understand their dark foundations. The halo model is the cornerstone of how cosmologists think about this structure. It is a beautifully simple yet powerful idea that breaks down the universe's complexity into manageable pieces. The model proposes that all the dark matter in the cosmos is partitioned into these halos, each with a specific mass and size. Ordinary matter, the gas that will become stars, then follows the gravitational blueprint. It falls into these pre-existing dark matter wells, cools down, and eventually condenses to form a galaxy at the halo's center. In this framework, a galaxy is not a standalone object. It is the luminous heart of a much larger, invisible body. The halo is the true entity, the galaxy is its brightest feature. This model allows scientists to make precise predictions. If you know the rules of gravity and the initial conditions from the cosmic microwave background, you can simulate how these halos should grow, merge, and distribute themselves across cosmic time. And what a range of halos there is! The scale is staggering. On the upper end, you have the Titans. These are the halos that host immense galaxy clusters containing the mass of 1,000 trillion suns. They are the grand central stations of the cosmic web, where thousands of galaxies swarm like bees, all held in the grip of a single, monstrous sphere of dark matter. Then there are the halos like the one hosting our Milky Way, with a mass of about 1 trillion suns. But for every giant, there are countless dwarfs. Simulations predict a vast population of smaller subhalos, clumps of dark matter that were themselves once independent halos, but were captured and now orbit within the gravitational domain of a larger one, like moons around a planet. Our Milky Way's halo should be teeming with hundreds of these dark matter satellites. This prediction leads directly to one of the most intriguing puzzles in modern cosmology. According to the halo model, many of these subhalos should be massive enough to pull in gas and form faint, dwarf galaxies. Yet when we look around our local cosmic neighborhood, we find far fewer dwarf galaxies than the number of subhalos predicted. Where are all the missing galaxies? Are these subhalos truly dark, devoid of stars, or does star formation in such tiny gravitational wells simply fail to ignite? This question presses directly on the nature of dark matter itself, probing the smallest scales of the cosmic map. The life story of a halo is written in collisions. They do not form in isolation. The halo model predicts a violent, hierarchical history of growth. In the early universe, countless tiny seed halos condensed from the primordial soup of dark matter. Over billions of years, gravity pulled them together. They merged, building up mass in a cosmic game of accumulation. A halo like our own is an archaeological site, its structure layered with the remnants of countless smaller halos it has consumed over its lifetime. Astronomers can read this history by studying the motions of ancient star clusters and streams of stars within our galaxy, the fossilized debris of those long-ago mergers. The distribution of halo masses across the universe today, from the rare giants to the abundant dwarfs, is a key fingerprint of our cosmological model. It tells us about the initial conditions of the universe and the rules of gravity that shaped it. When the Vera Rubin Observatory completes its census of millions of galaxies and their motions, it will provide an unprecedented ledger of halo masses, testing these predictions with real data. By studying the nodes of the network, we are learning to read the autobiography of the cosmos, written in the silent language of gravity. The blueprint for this entire cosmic story was written in the first fraction of a second. Before there was any matter, before there was even light, the universe underwent a period of unimaginable, faster-than-light expansion called inflation. This explosive stretching smoothed the cosmos to an almost perfect uniformity, but on the quantum scale, tiny fluctuations were inevitable. These were microscopic ripples in the fabric of spacetime itself, random variations in density that were smaller than a single atom. Inflation then magnified these quantum whispers to cosmic proportions, stretching them across the entire observable universe. Those minute differences, 1 part in 100,000, became the seeds for everything to come. They were the initial instructions, the faint pattern of slightly denser and slightly emptier regions imprinted onto the newborn cosmos. When the universe cooled and filled with particles, dark matter naturally pooled into those slightly denser spots. This is where the dark matter's nature gave it a decisive head start, because it does not interact with light or with itself through any force but gravity. It was free to begin collapsing under its own weight immediately. Ordinary matter, still a hot, raging plasma fused with radiation, was stuck. It could not fall into those gravitational wells because the intense pressure of light pushed back, creating those sound waves we discussed earlier. For those first few 100,000 years, dark matter worked alone in the dark, quietly gathering. The moment the universe became transparent and released the cosmic microwave background, that changed. The ordinary matter, now decoupled from the light, was finally free to answer gravity's call. It flowed into the gravitational foundations that the dark matter had already built. Think of it like the construction of a great city. First, the invisible infrastructure is laid down, the sewer lines and power grids and foundational pilings. Only after that framework is secure do the builders arrive to erect the visible buildings, the homes and towers that define the skyline. Dark matter laid the gravitational pilings. Ordinary matter built the luminous cities upon them. From this point, the growth of the cosmic web was a slow, relentless process of gravitational accumulation, a story told in 2 acts, collapse and merger. The very first structures to form were not grand galaxies, but tiny, dark matter microhalos. These were the primordial building blocks, each containing perhaps the mass of a small mountain, yet spanning a volume larger than our solar system. They were the first knots in the web. Gravity is a patient architect. Over hundreds of millions of years, these microhalos began to attract one another. They drifted together along the faint tendrils of the initial density field and merged, forming progressively larger halos. This is the principle of hierarchical structure formation, where small things build big things. It is a bottom-up assembly of the cosmos. As time flowed forward, the scale of the mergers grew. Those early halos merged into clumps the mass of dwarf galaxies. Those clumps, in turn, were drawn into the deepening gravitational wells along the emerging filaments of the web. You can see this process beautifully in cosmological simulations. When played as a time-lapse, the early universe looks like a sparse, faint fog. Then, pinpricks of light appear, not stars yet, but the first dense knots of dark matter. These pinpricks begin to move, streaming along invisible rivers toward one another. They merge in silent, ghostly collisions, their halos combining into larger, brighter knots. Filaments of matter slowly condense out of the fog, connecting these growing nodes into a delicate, cosmic lattice. It resembles watching frost crystals form on a window pane, starting with isolated specks that gradually branch and connect into a complex, beautiful pattern. But this pattern is in 3 dimensions and spans billions of light years. The lighting of the galaxies came later, as a direct consequence of this dark matter assembly line. When a dark matter halo reached a critical mass, its gravitational pull was strong enough to rapidly attract vast clouds of hydrogen and helium gas. This gas would rush in, collide, and heat to incredible temperatures before eventually cooling and fragmenting into the first generation of stars. In the simulations, this is the magical moment when the previously dark nodes of the web suddenly ignite with brilliant white light. The first stars did not form in isolation. They lit up along the entire growing network, tracing the filaments and highlighting the nodes. The web, once invisible, now had a luminous signature. The largest clusters, the intersections of many filaments, became the last to fully assemble. They are the cosmic metropolises, and they are still growing today as fresh filaments channel new galaxies into them. This entire multi-billion-year narrative, from quantum whisper to glittering web, ties our map directly back to its origin. The subtle patterns in the cosmic microwave background are not just a frozen snapshot. They are the opening frame of a movie whose final scene is the elaborate cosmic cartography we chart today. The invisible web is not a static sculpture. It is a living, growing entity, and we are witnessing a single frame in its long evolution. But the cosmic inventory held one more glaring discrepancy. Astronomers had mapped the dark matter and counted the stars, yet when they tallied all the ordinary matter, the baryons made of protons and neutrons that form everything we see, a huge portion was simply missing. Based on the precise measurements from the cosmic microwave background, we know exactly how much ordinary matter should have been created in the Big Bang. Yet when we add up all the atoms in all the stars, galaxies, and cold gas clouds we can observe, we come up short by about half. Where did the rest of the universe's normal material go? The answer was hiding in the emptiest places of all, the vast spaces between the galaxies. For decades, theorists predicted that the filaments of the cosmic web, those dark matter highways, should not be entirely dark. They should be threaded with an extremely diffuse fog of ordinary matter, gas so hot it glows only in X-rays, yet so thin it is nearly invisible. This is the warm-hot intergalactic medium, or WIMP. It is the universe's hidden reservoir, and finding it became a critical piece of the cosmic census. Detecting something so faint required a new kind of observation. Instead of looking for the gas to glow on its own, astronomers turned to cosmic lighthouses. They used the brilliant, distant beams of quasars, the ultra-luminous cores of ancient galaxies powered by supermassive black holes. As the intense light from a quasar travels billions of light years to reach us, it passes through the invisible filaments of the cosmic web. Atoms within the WIMP, like oxygen and neon heated to millions of degrees, can absorb very specific wavelengths of that background light. This leaves minuscule, telltale dips in the quasar's spectrum, like unique chemical fingerprints imprinted on the beam during its long journey. Spotting these absorption lines is like finding the silhouette of a faint ghost projected onto a brilliant spotlight. It requires exquisitely sensitive X-ray telescopes like Chandra and XMM Newton, instruments designed to catch these subtle spectral signatures. The hunt is painstaking, but it is working. By combining observations of multiple quasars whose lines of sight pierce through predicted filament structures, astronomers are slowly building a case. They are finding the predicted absorption lines, confirming that the great voids between galaxies are not empty at all, but filled with a tenuous, searing hot plasma. This gas is strung along the dark matter filaments like luminous dew on a spider's web, a faintly glowing counterpart to the invisible gravitational scaffolding. Discovering the WIMP does more than just balance the cosmic books. It completes our physical picture of the web, revealing it as a fully realized structure. The dark matter provides the gravitational skeleton. This warm, hot gas is the diffuse muscle and connective tissue flowing along it, and the galaxies are merely the bright, dense knots where that gas pooled, cooled, and ignited into stars. We are learning that what we call the universe, the glittering star fields and majestic spirals, is just the sparkling highlight reel. The true substance of the cosmos is a vast, faintly luminous fog, an architecture of shadow and soft X-ray light, with the galaxies we cherish serving as its most brilliant decorations. The maps we have now are merely the first blurry sketches of a hidden continent. To see its true form, we need sharper eyes and a wider view. A new generation of cosmic observatories is poised to give us exactly that, launching a revolution in our ability to chart the invisible. These are not just bigger telescopes, they are entirely new instruments designed to answer the most profound questions left on the map. Leading this charge is the Vera Rubin Observatory in Chile. Its centerpiece is the legacy survey of space and time, a project of almost unimaginable ambition. For 10 years, a gigantic 3.2 billion pixel camera will scan the entire southern sky every few nights. It will not just take pictures, it will create a deep, dynamical movie of the cosmos. The scale of its census is staggering. It will detect and measure the shapes of over 20 billion galaxies. This torrent of data will allow scientists to construct the most detailed weak lensing mass maps ever made, with enough galaxies to slice the universe into thin chronological layers. For the first time, we will watch the dark matter web evolve in 3 dimensions, seeing how filaments thicken and nodes merge across billions of years. This will let us measure the growth of cosmic structure with such precision that we can tightly constrain the nature of dark energy, the force accelerating the universe's expansion. Is dark energy a constant vacuum energy, or does it change over time? The subtle imprint on the web's growth will hold the answer. Meanwhile, from a vantage point a million miles from Earth, the Euclid Space Telescope is already at work. Its mission is specifically designed to map the geometry of the dark universe. While Rubin will watch from the ground, Euclid observes from the stillness of space, free from atmospheric blur. It carries 2 powerful instruments, one for visible light and one for near-infrared, to measure both the shapes of galaxies and their redshifts with exceptional accuracy. Euclid's goal is to create a 3-dimensional map covering more than a third of the sky, tracing the distribution of both dark matter and dark energy by combining weak lensing with another cosmic ruler, the Baryon acoustic oscillations. By comparing these 2 independent measurements, Euclid will perform a crucial test, checking if our theory of gravity, Einstein's general relativity, still holds perfectly on the largest cosmic scales, or if we see hints of a modification. Then, later this decade, NASA's Nancy Grace Roman Space Telescope will join this effort with a unique superpower, its enormous field of view in infrared light. Roman can capture an area of sky 100 times larger than the Hubble Space Telescope's famous deep fields in a single snapshot. This wide field is perfect for surveying vast swaths of the cosmos efficiently. Its infrared vision is key, allowing it to peer through the dust that obscures our view within our own galaxy, and to see the most distant, redshifted galaxies whose light has been stretched into the infrared part of the spectrum. Roman will conduct its own high-definition weak lensing survey, adding another independent, exquisitely precise data set to the global effort. The synergy between these observatories will be transformative. Rubin provides the immense time-lapse volume from the ground. Euclid offers space-based precision and a dedicated geometry mission. Roman delivers wide-field infrared depth. Together, they will cross-check and reinforce each other's findings, eliminating systematic errors and building an irrefutable, multi-wavelength portrait of the shadow cosmos. For the first time in history, we will possess high-fidelity, 3-dimensional dark matter maps covering most of the observable sky. This is not just an incremental improvement. It is the difference between a hand-drawn sketch of a mountain range and a satellite topographic map. With this new clarity, we will not just see the web, we will measure its tension, trace its flows, and subject our most fundamental theories to a trial by data. We will ask the cosmos directly, what is the dark energy that stretches the web, and does gravity itself behave as we expect across the vast emptiness between its threads? Light, for all its brilliance, is only one messenger from the cosmos. The universe speaks in many languages, and to hear its full story, we must learn to listen with new ears. This is the dawn of multi-messenger astronomy, where we combine the whispers of gravitational waves, the faint trails of neutrinos, and the ancient light of photons to build a single, unified map of reality. While these new signals do not detect dark matter directly, they provide powerful, independent cross-checks on the very cosmic distances and structures that our dark matter models seek to explain. It is like triangulating the location of a hidden city by listening to echoes from different directions. The first of these new messengers arrived not as light, but as a ripple in space-time itself. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting the faint chirp of two black holes colliding over 1 billion light-years away. This was the first direct observation of gravitational waves, confirming a century-old prediction of Einstein and opening an entirely new window on the universe. Unlike light, which can be absorbed, scattered, or blocked by dust, gravitational waves pass through almost everything unimpeded. They are a pristine signal of the most violent events in the cosmos. The detectors, like LIGO in the United States and Virgo in Italy, are some of the most sensitive instruments ever built. They work by measuring minute changes in the length of two perpendicular arms, each several kilometers long, using laser light. A passing gravitational wave stretches one arm while compressing the other, shifting the laser's interference pattern by a distance smaller than the width of a proton. It is an almost unimaginable feat of precision. So how do these ripples help us map the cosmic web? The key lies in what astronomers call standard sirens. When LIGO and Virgo detect the merger of two neutron stars, the dense, city-sized remnants of dead suns, they measure the specific waveform of the gravitational waves. This waveform tells scientists the intrinsic strength of the event, how powerful the cosmic crash truly was. By comparing that intrinsic strength to how faint the signal appears when it reaches Earth, astronomers can calculate the distance to the merger with remarkable accuracy, independent of any other method. It is analogous to knowing the true wattage of a light bulb. If you see how dim it appears from far away, you can deduce exactly how far you are standing from it. This provides a new, direct ruler for measuring cosmic expansion. When such an event is also observed with traditional telescopes, pinpointing its host galaxy, we get a powerful cross-check. We can compare the distance from the gravitational wave siren to the distance inferred from the galaxy's redshift. Any discrepancy could reveal subtle biases in our measurements of the large-scale structure, the very fabric that dark matter weaves. It is a clean, independent test of the cosmic distance ladder, ensuring our map of the expanding universe, and by extension the dark matter within it, is drawn to scale. Meanwhile, from the pristine ice deep under the South Pole, another silent messenger is being captured. The IceCube Neutrino Observatory is not a telescope in any traditional sense. It is a cubic kilometer of Antarctic ice instrumented with thousands of sensitive light detectors. Its quarry is the neutrino, a ghostly fundamental particle so elusive that trillions pass through your body every second without a single interaction. Neutrinos are produced in the hearts of stars, in the violent aftermath of supernova, and in the jets of active black holes. Because they barely interact with matter, they travel in perfectly straight lines from their sources, offering a direct pointer back to the most energetic engines in the universe. In 2017, IceCube detected a single high-energy neutrino and alerted astronomers worldwide. Within moments, telescopes swiveled to the direction it came from and found a brilliant, flaring blazar, a supermassive black hole at the core of a distant galaxy, shooting a jet of radiation directly at Earth. This was the first time a neutrino was traced to a specific cosmic source, proving the potential of this new messenger. For cartographers of the invisible, neutrinos offer a different kind of check. By building a population of these cosmic tracers and mapping their origins, we can study the distribution of the universe's most extreme accelerators. Are they clustered along the filaments of the cosmic web? Do they avoid the vast voids? This statistical map of cataclysm can be compared to the map of mass from weak lensing. Do the most violent events in the universe happen where the dark matter is densest? This multi-messenger approach creates a form of cosmic consensus. When the map from bent starlight, the map from galaxy clustering, the distances from gravitational wave sirens, and the tracer map from neutrinos all tell the same story about the large-scale structure and expansion history of the universe, our confidence in the underlying model, including the role of dark matter, grows exponentially. If they disagree, it points to a profound mystery, a crack in our understanding that could lead to the next great discovery. We are no longer just watching the cosmos. We are listening to its vibrations and feeling the passage of its most elusive particles, weaving every thread of evidence into a stronger, more complete tapestry of the real. The cosmic map we have charted is not a static blueprint, it is a story of constant conversation. The invisible web does not merely hold galaxies in place, it actively raises them, nurtures them, and is in turn reshaped by their fiery lives. This is a profound symbiotic relationship, a gravitational dance where both partners influence each other's fate across billions of years. It begins with a simple, powerful act of creation. A dark matter halo forms, its gravity creating a deep well in the fabric of spacetime. Vast rivers of primordial hydrogen and helium gas flowing along the cosmic filaments are channeled into this well. As the gas falls in, it collides and compresses, heating to incredible temperatures, often reaching millions of degrees. For a galaxy to be born, this gas must cool. It does so by radiating away its heat in the form of X-rays and ultraviolet light. As it cools, the gas loses its supporting pressure, condenses further, and eventually fragments into dense clouds. Within these clouds, gravity takes over on a smaller scale, pulling matter together until the pressures and temperatures at the core ignite nuclear fusion. The first star flickers to life and a galaxy is born. The dark matter halo provided the essential nursery, a gravitational cradle without which this process could never have begun. But the story does not end with a single ignition. It becomes a cycle of feedback, a cosmic dialogue between the invisible and the luminous. The stars that form are not gentle neighbors. Massive stars live fast and die young, exploding as supernova in catastrophic blasts that flood their surroundings with energy and newly forged heavy elements. At the center of most galaxies, a supermassive black hole lurks, and when it actively feeds on surrounding gas, it becomes an active galactic nucleus, shining with the power of 1 trillion stars and driving colossal winds. These tremendous outflows from stars and black holes act like cosmic regulators. They heat the surrounding gas, preventing it from cooling and forming new stars too quickly. In extreme cases, they can even blow vast quantities of gas entirely out of the halo, starving the galaxy of future fuel. This stellar and black hole feedback is the reason our universe is not one giant blazing ball of stars. It paces the growth of galaxies, ensuring they evolve over billions of years rather than consuming all their fuel in a brief, glorious burst. This is where the relationship becomes truly symbiotic, because this energetic feedback does not just affect the gas, it can also influence the dark matter itself. While dark matter particles do not feel electromagnetic forces and pass through each other like ghosts, they are still subject to gravity. When a powerful supernova explosion or a quasar wind pushes a huge mass of ordinary matter out of the central regions of a galaxy, the gravitational landscape of the entire halo subtly shifts. The sudden removal of that mass can cause the dark matter distribution to expand slightly or readjust. It is a minuscule effect on the invisible web, but over billions of years and countless stellar generations, this gravitational conversation leaves an imprint. To understand this intricate dance, scientists have moved beyond dark matter-only simulations. They now run full-scale hydrodynamic simulations that model not just gravity, but the complex physics of gas, star formation, supernova, and black holes. Projects like IllustrisTNG and IllustrisTNG are virtual universes where this entire life cycle plays out. Watching these simulations is witnessing a galaxy's biography. You see a dark matter halo condense from the web. You watch gas flow in, cool, and ignite into a glittering pinprick of stars. Then, as the first massive stars die, you see brilliant bubbles of energy expand from the young galaxy, heating the nearby gas and temporarily quenching further star formation. The central black hole grows, occasionally flickering to life and launching jets that punch far beyond the galaxy's edge. The result is a galaxy whose final size, shape, and star formation history are a direct product of this ongoing negotiation between the pull of the dark matter and the push of its own stellar engines. The invisible web is far from a passive scaffold. It is an active participant, a gravitational partner in a billion-year-long tango that determines whether a galaxy becomes a majestic spiral like our Milky Way, a quiescent elliptical, or a faint dwarf. Our own existence is a product of this delicate balance, a testament to a universe built on conversation between the seen and the unseen. The gravitational map is a stunning achievement, but it is not the final answer. It tells us where the shadow is, but not what casts it. To solve that deeper mystery, physicists have embarked on a parallel quest, moving from cosmic cartography to particle hunting. Their goal is to capture the elusive substance itself, not just its silhouette. This search unfolds in two distinct arenas, one waiting in profound silence deep within the Earth, and the other scanning the heavens for a telltale flash of something amiss. The first path is direct detection. Imagine trying to hear a single, perfect note played in a stadium during a roaring concert. That is the challenge facing experiments like LUXZEP-LIN in a former gold mine in South Dakota and XENONNT under the Gran Sasso Mountain in Italy. Their method is one of extraordinary patience and shielding. They are built over a mile underground, where thousands of feet of solid rock filter out the constant rain of cosmic rays that would overwhelm any signal. At their heart are immense, ultra-pure vats of liquid xenon, chilled to extreme temperatures. The hope is that once, perhaps in a year, a dark matter particle from the halo surrounding our Milky Way will drift through the tank and do the impossible, bumping into the nucleus of a xenon atom. This collision would release a tiny flash of light and a whisper of electric charge, a signature that teams of scientists monitor around the clock. They are listening for a sound the universe has never made before. The connection to our map is direct. These experiments rely on the predicted density of dark matter in our local galactic neighborhood. Every model of the Milky Way's halo informs their expectations for how many particles should be passing through their detector every second. The profound silence so far, the absence of a confirmed bump, is itself a powerful result. It tells us that if dark matter is a WIMP, it must be even more ghostly, interacting even more weakly than our best models predicted, forcing us to refine the search. When the map says the river of dark matter should be flowing thick and the detector hears nothing, we must reconsider the nature of the water itself. While some hunt for the direct whisper, others search for an echo of destruction in the sky. This is the path of indirect detection. The theory is compelling. If dark matter particles are their own antimatter counterparts, they might annihilate one another when they collide within the dense cores of halos. Or perhaps over cosmic timescales they decay. Either process would produce a shower of secondary particles we can see, like gamma rays, neutrinos, or unusual cosmic rays. Telescopes become forensic instruments. scanning regions where our map says dark matter should be most densely packed, looking for an anomalous glow that cannot be explained by any known astrophysical source. The favorite hunting grounds are the hearts of nearby galaxies, including our own Milky Way center and the dwarf spheroidal galaxies that orbit it. These faint, ancient star clusters are considered pristine laboratories because, according to the cosmic web model, they are dominated by dark matter with very little of the messy stellar activity that produces confusing background signals. When the Fermi Gamma Ray Space Telescope points at a dwarf like Reticulum II or Draco, it is testing a specific prediction from the map, the expected gamma ray flux from annihilations occurring within its dense dark matter core. A subtle, unexplained excess there would be a potential smoking gun. Similarly, neutrino telescopes like IceCube scan the galactic center, watching for a directional excess of these ghostly particles that could trace back to dark matter annihilations. So far, no definitive signal has emerged, but each anomalous flicker, each unexplained data point, sends theorists back to their calculations to adjust the properties of the hypothetical particle. The map guides the hunt, telling us where to look, and the hunt, in turn, refines the map, testing our assumptions about how dark matter behaves in the densest knots of the cosmic web. We are closing in from both sides, from the depths of the Earth and the edge of space, hoping for a single, consistent signal that will finally give a name to the architect of the invisible universe. This entire journey forces us to confront a profound question about the nature of knowledge itself. How can we claim to know something we cannot see, touch, or directly sense in any way? The philosopher of science Bas van Frossen once framed a powerful challenge, arguing that science aims not for a true description of the world, but merely for theories that are empirically adequate, that save the phenomena we observe. From this view, dark matter could be seen as a convenient fiction, a mathematical placeholder that makes the equations of galaxy rotation and lensing work without necessarily being real. It is a compelling philosophical stance that reminds us to stay humble, yet the scientific case for dark matter's reality does not rest on a single convenient equation. Its power comes from a phenomenon known as the consilience of evidence. This is the convergence of multiple, independent lines of inquiry onto the same startling conclusion. Think of it like a detective building a case not from one piece of circumstantial evidence, but from a dozen unrelated witnesses who all tell the same story. The bending of light from gravitational lensing tells us where mass is concentrated. The frozen ripples in the cosmic microwave background tell us how much total matter existed in the infant universe and how it was distributed. The motions of stars within galaxies tell us that invisible mass grips them. The separation of mass from gas in colliding clusters tells us this substance is physically distinct. And the growth of cosmic structure in supercomputer simulations tells us how such a substance would evolve over time. None of these methods measures dark matter directly. Each one measures its gravitational shadow, its effect on the things we can see. The miracle is that all these different shadows, cast from different angles and across different epochs, all align to outline the same hidden object. They converge to describe a cosmos where an invisible, cold, collisionless substance forms a vast web, providing the gravitational foundation for every galaxy. This is not a single assumption patching one hole. It is a single explanation weaving together a tapestry of disparate cosmic mysteries. It challenges our most basic, sensory-based intuition about what is real. Our brains evolved to trust what we can see and touch. Science, however, is a tool that extends our senses, building instruments that see in X-rays, feel gravitational ripples, and count ghostly neutrinos. It employs logic and mathematics as a new form of perception. The map of the dark matter web is a triumph of this extended cognition. It demonstrates that reality is not limited to what is immediately apparent, that the true architecture of the universe can be hidden in plain sight, waiting to be decoded through reason, patience, and the collective ingenuity of countless minds across generations. This reshapes our cosmic self-perception in a fundamental way. We are not just beings living on a rocky planet orbiting an ordinary star. We are creatures whose curiosity has allowed them to perceive the hidden skeleton of all creation. We inhabit the luminous nodes of a shadowy vastness, and through science we have begun to trace its contours. The map of the invisible is ultimately a map of the reach of the human intellect, a testament to our ability to uncover deep truths about a reality far stranger than our senses alone could ever reveal. The profound story of this invisible map demands to be told. While the science is complex, its wonder is universal, and a dedicated movement of scientists, artists, and educators is working tirelessly to bring the cosmos down to Earth for everyone. This is not just about sharing facts, it is about sparking a sense of shared discovery, transforming abstract data into experiences that resonate. One of the most powerful portals to this hidden universe is the modern planetarium. Gone are the simple star projectors of the past. Today's digital domes are immersive theaters of the mind, capable of flying audiences through the very supercomputer simulations we discussed. You do not just hear about the cosmic web, you soar along its golden filaments, watching galaxies ignite at the intersections, feeling the scale of billions of light-years shrink to a human journey. These shows, crafted by teams of astrophysicists and visual storytellers, translate petabytes of data into a visceral, emotional experience. They make the invisible architecture not just understandable, but breathtakingly real. For those exploring from home, the digital frontier offers its own wonders. Interactive online visualizations, often built from real survey data, allow anyone with a web browser to become a cosmic cartographer. You can rotate three-dimensional maps of galaxy clusters, peel away layers of the universe to see different epochs, or zoom into the intricate structure of a simulated dark matter halo. These tools democratize discovery, putting the universe's blueprint at the public's fingertips. This spirit of shared exploration reaches its zenith in citizen science projects. Initiatives like Galaxies harness the pattern recognition power of human curiosity on a global scale. Volunteers from all walks of life log on to examine images from telescopes like Hubble and Sloan. Their task is beautifully simple: classify the shapes of galaxies. Is it a spiral, an elliptical, or something merging? This human-powered classification is something computers still struggle with, and it provides invaluable data for astronomers studying how galaxy types correlate with their dark matter environments. Hundreds of thousands of people have contributed, making genuine discoveries like the now famous green pea galaxies along the way. It turns the act of mapping the cosmos into a collective human endeavor. On social media, outreach specialists and scientists themselves are breaking down barriers. Through short, engaging videos on platforms like TikTok and Instagram, they use everyday analogies, striking visuals, and clear, enthusiastic explanations to unpack concepts like gravitational lensing or the cosmic web. They answer questions directly, demystifying the process of science and showing the human faces behind the research. This approach does more than inform; it builds a community of wonder. It invites everyone to look up and ponder the same profound mysteries. The goal of all this outreach is multifaceted. It captivates the public imagination, reminding us that the universe is far stranger and more magnificent than our daily lives suggest. It inspires the next generation of scientists, engineers, and dreamers, showing them that career paths exist where curiosity is the primary fuel. Perhaps most importantly, it fosters a society that values fundamental exploration. Understanding how we map the invisible web reinforces why we fund great observatories and support basic research. It cultivates an appreciation for the long, collaborative, and often difficult pursuit of knowledge for its own sake, a pursuit that tells us not only where we are in the cosmos, but expands what we are capable of understanding together. The search for invisible threads in the cosmos has woven a new fabric of innovation here on Earth. The same tools that decode the universe's hidden architecture are quietly transforming fields far beyond astronomy, creating a cascade of practical benefits that touch our daily lives. This journey into the cosmic dark has, perhaps unexpectedly, become a powerful engine for technological progress. Consider the sheer scale of data involved. Projects like the Vera Rubin Observatory will generate more raw data in a single night than the entire astronomy community produced in the first century of its existence. This is not just a lot of information, it is a tidal wave that would overwhelm traditional methods of analysis. To navigate this deluge, scientists were forced to become pioneers in big data. They developed new ways to store, process, and transmit petabytes of information, creating robust data pipelines and compression algorithms that are now being adapted for everything from genomics to climate modeling. The challenge of finding a subtle lensing signal in billions of galaxy images pushed machine learning to its limits, leading to the creation of more sophisticated neural networks that can recognize complex patterns in noisy data. These same algorithms are now being used to improve medical diagnostics, helping radiologists spot early signs of illness in scans by learning to see patterns invisible to the human eye. They optimize supply chains, predict equipment failures in factories, and even help self-driving cars navigate complex environments. The quest to map the shadow universe has sharpened the very tools we use to understand our own world. The hardware born from this cosmic search is equally transformative. To detect the faintest whispers of the cosmos, engineers must build instruments of almost impossible sensitivity. The charge-coupled devices in modern telescopes, designed to capture single photons from the edge of the observable universe, rely on semiconductor technology that has directly improved the image sensors in every smartphone and medical endoscope. The exquisite mirrors and lenses, polished to atom-level smoothness to avoid scattering light, have advanced the entire field of precision optics, benefiting manufacturing and laser technology. Perhaps most remarkably, the struggle to shield dark matter detectors from background radiation has led to breakthroughs in creating ultra-pure materials and extraordinarily quiet sensors. These technologies are finding new purpose in safeguarding human health. The same cryogenic systems that keep detectors at a fraction of a degree above absolute zero are being adapted for more efficient magnetic resonance imaging machines. The advanced sensors developed to listen for a dark matter particle's bump could one day be used to detect trace contaminants in water supplies or identify specific chemical signatures in a patient's breath for early disease detection. Even the image processing software, crafted to measure the tiny gravitational shears of weak lensing, is being repurposed. Its ability to discern true signal from noise in a messy image is now helping archaeologists enhance faded inscriptions on ancient artifacts and allowing conservationists to monitor minute changes in fragile ecosystems from satellite photos. The line between exploring the cosmos and improving life on our planet is far thinner than it appears. This flow of innovation from the stars to the street is not a happy accident. It is a fundamental feature of ambitious, curiosity-driven science. When you set out to solve a problem as profound as mapping the invisible mass of the universe, you cannot simply order the tools you need from a catalog. You must invent them. This process of invention, driven by a need to see the unseeable, inevitably spills over into other domains. The global internet, for instance, has roots in the need for scientists to share large data sets across continents, a challenge familiar to every cosmology collaboration today. The pursuit of pure understanding builds a foundation of new knowledge, techniques, and technologies that others can then build upon for entirely different purposes. Investing in the map of the cosmic web is, in a very real sense, an investment in our own technological future. It cultivates a workforce skilled in cutting-edge computing, materials science, and data analytics. It drives the development of infrastructure like high-speed networks and supercomputing centers that become national assets. The story of dark matter is more than a tale of hidden cosmic forces. It is a testament to how asking the biggest questions can lead to some of our most practical and profound advancements, weaving the threads of discovery into the very fabric of our society. The great maps of the cosmos are signed by all of humanity. This cartography of the invisible is not the work of a lone genius in an observatory dome, but of a vast, distributed network of minds and machines spanning the globe. From the high deserts of Chile to the frozen plains of Antarctica, from European laboratories to supercomputers in Japan, the effort to chart the dark web is a testament to what we can achieve together. Projects like the Dark Energy Survey operate on this principle of collective intelligence. Its powerful 570-megapixel camera, DECAM, sits atop a telescope in Chile, but its heart beats in collaboration. Over 400 scientists from more than 25 institutions across 7 countries designed the instrument, planned the 6-year survey, and now analyze the flood of data. They do not hoard their findings, they release vast public data sets to the world, allowing anyone from a professional astronomer to a curious student to mine the cosmos for new discoveries. This open-source model of science accelerates understanding, turning a single telescope into 1,000 eyes. Similarly, the Planck satellite, which mapped the cosmic microwave background with exquisite precision, was a mission of the European Space Agency, but its data was analyzed by a consortium of hundreds of researchers from dozens of nations. The resulting map of the infant universe, a cornerstone of modern cosmology, carries no flag. It belongs to every person on Earth. The upcoming Vera Rubin Observatory embodies this spirit on an even grander scale. Funded by the United States National Science Foundation and the Department of Energy, its construction and operations involve key contributions from Chile, the United Kingdom, and an international consortium of other partners. Its 10-year legacy survey of space and time will produce a data set so valuable it is considered a global astronomical infrastructure, a digital sky that will fuel research for generations. This model works because the questions are too big for any one team. Mapping the dark universe requires expertise in particle physics, astrophysics, statistics, computer science, and advanced engineering. It needs theorists to build models, observers to collect light, and data scientists to find the signal in the noise. By pooling resources and sharing knowledge across borders, we build instruments more powerful than any single nation could afford and solve problems faster than any isolated group could manage. This global endeavor does more than produce charts, it weaves a fabric of shared purpose. In a world often divided, the silent, patient work of understanding our place in the cosmos stands as a powerful counterpoint. Scientists from countries with deep political disagreements work side by side on these collaborations, united by a common curiosity that transcends earthly conflicts. They are driven not by national interest but by a human desire to know. The legacy they create is not a weapon or a commodity, but a story, a deeper narrative of where we came from and what the universe is made of. This shared narrative, written in data and decoded by thousands, becomes a common heritage. When we look at that map of the cosmic web, we are not looking at an American map or a European map. We are looking at humanity's map, a product of our collective wonder and perseverance, a reminder that our greatest achievements begin when we look up together. Our most detailed maps still have edges that fade into mystery. The cosmic web we have charted is magnificent, yet it is a map drawn with the ink of gravity alone, and we must admit there are entire realms of possibility our current charts cannot yet depict. What if dark matter, this ghostly substance, is not as simple and featureless as our standard model assumes? Could it possess its own hidden complexity, a rich internal structure we have not yet imagined? Some theorists are exploring the provocative idea that dark matter might not be entirely dark to itself. In models of self-interacting dark matter, these particles could experience a new, weak force that only acts between them, allowing them to scatter off one another like billiard balls in the depths of a halo. This subtle interaction could solve persistent puzzles in our map, like the core cusp problem. The gentle friction from these self-collisions might smooth out the predicted dense peaks at the centers of dwarf galaxies, creating the softer cores that observations suggest. It is a fascinating possibility, a shadow universe with its own faint, unseen weather. Or perhaps the darkness is not monolithic at all. Just as the ordinary universe is built from a diverse zoo of particles, from electrons to neutrinos to quarks, could there be a whole hidden sector of dark matter particles? We casually speak of it as one thing, but it might be a family. There could be multiple species with different masses and properties, some colder and some warmer, all weaving together to form the web we detect. This idea opens up wild speculative landscapes. Could there be dark atoms bound by a dark electromagnetic force? Could there even be dark stars or dark planets, entire structures made from this hidden substance, forever invisible to our telescopes but gravitationally shaping the luminous galaxies we see? While this sounds like science fiction, it is a serious line of theoretical inquiry, reminding us how little we truly know about the substance that forms 85% of the universe's matter. Our tools themselves have inherent limits. The largest cosmological simulations are marvels, but they still model the universe with a finite number of particles in a finite box. They cannot capture every single tiny subhalo or the most delicate threads of the web. Our grand surveys, like the upcoming Legacy Survey of Space and Time, will map billions of galaxies, but that is still a census of the brightest nodes in the network. The faintest dwarfs, the most diffuse filaments of gas, and the earliest, smallest structures remain below our detection threshold. We are mapping the continents of the invisible world, but we have yet to chart its archipelagos or its deepest ocean trenches. Furthermore, our entire understanding is filtered through the lens of gravity. It is the only language dark matter has used to speak to us so far. What if it whispers in other ways we have not learned to hear? This is where the most exotic theoretical ideas emerge, not as replacements for our map, but as sketches for its blank regions. One compelling proposal is fuzzy dark matter. In this model, the particles are incredibly light, billions of times lighter than an electron, so light that their quantum wave nature becomes important on galactic scales. Instead of behaving like discrete particles, this dark matter would act like a coherent wave flowing through the cosmos. Such a wave-like substance would naturally suppress the formation of structure on very small scales, potentially explaining why we see fewer tiny dwarf galaxies than our standard simulations predict. It would paint the cosmic web with a slightly softer brush, blurring the finest details. Another frontier is the question of what happened before the first dark matter halos formed. What were the very first structures to emerge from the primordial darkness? Were they strange, temporary waves or long-vanished dense knots? Our simulations can only extrapolate back so far before the physics becomes uncertain. To stand before this vast unknown is not a sign of failure, it is the essential condition of science. Every blank space on the map is an invitation. Those puzzling discrepancies between our predictions and observations are not errors, they are guideposts, flashing arrows pointing toward deeper physics. The missing satellite problem, the curious cores of dwarf galaxies, the precise way filaments connect, These are the clues that will lead us to the next revolution in understanding. Our current map, for all its beauty and precision, is a snapshot in an epic story of exploration that is far from over. The greatest thrill lies not in what we have charted, but in the profound mystery that remains, a darkness that still holds secrets about the fundamental nature of reality itself. The invisible web is more than a map of the present. It is a clock ticking toward the universe's final hour. For decades, cosmologists believed they knew the ultimate fate of the cosmos. The gravitational pull of all the matter in the universe, especially the immense weight of the dark matter web, was expected to act like a cosmic brake, gradually slowing the expansion that began with the Big Bang. The great question was whether that brake was strong enough to one day halt the expansion entirely, leading to a cataclysmic reversal known as the Big Crunch, or if the universe would simply coast forever toward a cold, dark, but stable end. The answer depended on a precise measurement of the cosmic ledger, a final accounting of the total mass contained within the filaments and halos we had worked so hard to chart. Then, in the late 1990s, two independent teams of astronomers made a measurement that shattered this entire framework. They were not looking at dark matter directly, but at distant stellar explosions called Type 1, a supernova. These are cosmic standard candles, explosions so uniform in their intrinsic brightness that by measuring how dim they appear, you can gauge their distance with incredible accuracy. What these teams found was utterly perplexing. The most distant supernova, whose light had been traveling for billions of years, were fainter than expected. This meant they were farther away than our models predicted. The expansion of the universe was not slowing down under gravity's pull, it was speeding up. It was as if you threw a ball into the air, and instead of falling back down, it shot away faster and faster into the sky. This discovery, which earned the Nobel Prize, demanded a radical explanation. Something was overpowering the collective gravitational attraction of all the dark and ordinary matter in the cosmos. That something was given a name: dark energy. Think of the cosmic web as a vast, intricate sculpture made of dark matter, with galaxies embedded in it like jewels. Now imagine this entire sculpture is sitting on a sheet of rubber that is being stretched in all directions at an ever-increasing rate. That stretching force is dark energy. It is not a substance that clumps like matter, but a property of space itself, a repulsive pressure that causes the very fabric of the cosmos to expand at an accelerating pace. The fate of the universe is now understood as a cosmic tug-of-war between two invisible giants. On one side is the dark matter web, with its immense gravitational pull, trying to hold the universe together, to pull galaxies closer and maintain the grand architecture. On the other side is dark energy, the relentless repulsive force, pushing everything apart and stretching the space-time in which the web is embedded. Which force will win dictates our ultimate destiny. Our current measurements suggest a universe in which dark energy has already gained the upper hand. The data from the cosmic microwave background, the large-scale structure maps, and the supernova all converge on a startling recipe for the cosmos. About 68% of the universe's total energy budget is dark energy. About 27% is dark matter, and a mere 5% is all the ordinary matter, the stars, planets, and us. This means the fate of our magnificent cosmic web is likely a slow, cold, and lonely one. In a scenario cosmologists call the Big Freeze or heat death, the acceleration will continue unchecked. Over trillions of years, the repulsive push of dark energy will stretch the cosmic web to its breaking point. First, the connections will sever. Galaxies that are not already bound in tight local groups will be carried away from one another by the expanding space faster than light can bridge the gap, vanishing over a cosmic horizon. Later, even the gravitationally bound structures will be challenged. The dark energy-stretched spacetime may grow so dominant that it overwhelms the gravity holding individual galaxies and clusters together. Stars will be pulled from their galaxies, planets from their stars, and eventually, the very fabric of matter itself may be torn apart in a far future event known as the Big Rip. This is the prophecy written into our gravitational maps. By meticulously measuring the growth of the dark matter web over cosmic time, we are taking the universe's pulse. Is structure forming at the rate we expect if dark energy is a constant force, or does the growth tell a different story? The subtle details in how clusters of galaxies assemble, how filaments thicken, and how voids grow provide a direct test. If dark energy's strength has changed over the eons, it will leave an imprint on the web's architecture. The map of the invisible is therefore a historical record, a current snapshot, and a predictive tool all at once. It tells us that the very structures we have learned to trace are engaged in a silent, slow-motion struggle against the emptiness of space itself. We are mapping a masterpiece that is, on the timescale of the cosmos, already beginning to fade. This profound struggle between shadow and void finds an echo in the human heart. Long before telescopes revealed the cosmic web, our species was already telling stories about invisible worlds. We have always sensed there was more to reality than meets the eye, from ancient spirits in the wind to the hidden forces of fate. Today, the scientific discovery of dark matter and its vast architecture has ignited a new chapter in this timeless tradition, becoming a powerful muse for artists, musicians, and storytellers. They are translating the data into experiences we can feel, building a vital bridge between the equations of cosmology and the language of human emotion. In galleries and concert halls, the invisible web is becoming sensory. Data sculptors and digital artists take the vast numerical outputs from simulations like IllustrisTNG and transform them into immersive installations. You do not just see the cosmic web, you stand inside it. Projections of golden filaments stretch across walls and floors, while ambient soundscapes translate the statistical distribution of dark matter halos into haunting, evolving music. The artist Rafik Anadol, for instance, uses machine learning to process vast astronomical datasets, creating breathtaking fluid visuals that feel like a journey through the universe's hidden memory. These works are not mere illustrations, they are interpretations. They ask us to experience scale and mystery directly, bypassing the intellect to stir a sense of awe that a graph alone cannot provide. They make the profound abstraction of dark matter tangible, something you can almost reach out and touch. This creative dialogue flows powerfully into narrative. Science fiction authors have long woven the cosmos into their tales, but dark matter offers a uniquely fertile ground. Writers like Liu Cixin, in his monumental Remembrance of Earth's Past trilogy, imagine civilizations so advanced they can manipulate the very structure of spacetime, engaging in warfare across dimensions we cannot perceive. This echoes the idea that dark matter could host its own complex physics, a hidden landscape operating by rules beyond our own. Other stories explore more intimate possibilities. What if life could evolve within a diffuse dark matter halo, beings made of something other than atoms, perceiving a universe where stars are mere faint disturbances in their luminous realm? These narratives do more than entertain, they stretch our conceptual frameworks. They force us to question the arrogance of assuming our kind of matter, our kind of life, is the only kind that could exist. They take the scientific what if and explore its philosophical and emotional consequences, preparing our minds for possibilities that future discoveries might reveal. This cultural resonance is not a one-way street. It creates a vital feedback loop with science itself. When a filmmaker crafts a visually stunning representation of a black hole, as in Interstellar, it shapes the public's imagination and fuels interest in the real astrophysics. When a novelist grounds a wild premise in rigorous scientific concepts, it educates while it enthralls. These artistic interpretations generate a cultural vocabulary, a set of shared images and ideas that make complex science discussable at the dinner table. They pull dark matter out of the specialized journal and into the realm of shared myth and wonder. This, in turn, builds public support for the grand, expensive projects that create the maps because people feel a connection to the story being uncovered. They are not just funding data points, they are funding a new chapter in humanity's oldest story, the quest to understand our place in the grand scheme. Ultimately, this flourishing of art and story around dark matter speaks to a deep human need. Science gives us the map, but art gives us the meaning. It addresses the visceral reaction to learning that most of the universe is hidden from us, that we are literally in the dark. Artists and writers metabolize that startling fact, transforming the potential anxiety of the unknown into a source of beauty, mystery, and creative inspiration. They remind us that curiosity is not purely analytical, it is also profoundly aesthetic. The drive to map the invisible web and the drive to sing about it, paint it, or write stories about it spring from the same source, a desire to connect with something larger than ourselves. In this ongoing dialogue, the cold, dark cosmos of the physicist and the warm, meaning-seeking heart of the human find a common ground, woven together in our endless attempt to render the invisible in some way seen. But this grand project of cosmic cartography is not conducted in a vacuum. It is a human endeavor, and like all profound undertakings, it carries with it a set of profound responsibilities. The quest to map the invisible web is a pinnacle of what we call big science, projects of immense scale, cost, and collaboration. And with that scale comes a need to look not only outward at the stars, but inward at our own choices. The first responsibility is to our own planet. Building and operating the Vera Rubin Observatory, the Euclid Space Telescope, or vast supercomputing centers requires significant resources. The concrete, the steel, the energy to cool server farms and power giant mirrors all leave a footprint. Recognizing this, the scientific community behind these projects has made environmental stewardship a core part of their mission. The Rubin Observatory, for example, was designed with sustainability in mind, using advanced insulation and cooling systems to minimize energy use in the arid Chilean desert. Its operations are planned to maximize efficiency, reducing the need for travel through remote collaboration tools. The goal is to ensure that our window on the universe does not come at an unacceptable cost to the world we observe it from. This mindfulness extends to the digital realm. The powerful artificial intelligence and machine learning tools forged to sift cosmic data are dual-use technologies. The same algorithms that find dark matter filaments in telescope images could, in different hands, be used for surveillance or social control. The ethical development and open discussion of these tools is therefore critical. The teams behind these AI systems are increasingly adopting principles of transparency, publishing their methods and often their code, inviting scrutiny and encouraging their use for beneficial purposes like medical research or climate modeling. They are building tools for discovery, not for dominion. Perhaps the most vital ethical commitment is to the principle that the cosmos belongs to everyone. The data from these monumental surveys is treated as a global public good. After a proprietary period for the teams who built the instruments, the petabytes of images and catalogs are released freely to the world. This policy is transformative. A graduate student in India or a dedicated amateur astronomer in Brazil can download the same data as a professor at a wealthy institution and make their own discoveries. It democratizes exploration, ensuring that the next brilliant insight can come from anywhere. This open access model actively fights against a new kind of scientific inequality, where the ability to ask questions of the universe is limited by national budgets. It fosters a truly global community of curiosity, yet this leads to the deepest ethical question. In a world facing immediate crises, climate change, poverty, conflict, why should we invest billions and immense human talent in mapping invisible structures billions of light years away? The answer is not found in a direct, practical payoff, but in the long-term architecture of human progress. Fundamental science like this is the foundation upon which all future technology is built. The quest to understand gravity gave us satellites and GPS. The study of electromagnetism gave us the entire digital age. We cannot predict which insight from mapping the dark universe will seed the revolutions of tomorrow, but history shows it inevitably will. More importantly, this pursuit cultivates something essential within us, a culture of evidence-based reasoning, humility before the unknown, and a shared sense of wonder that transcends borders. It answers a deep human need to understand our context, to know the story of which we are a part. Investing in the map of the cosmic web is an investment in the most valuable resource we have, our collective capacity to wonder, to reason, and to see beyond the horizon of our immediate needs. It is a declaration that our future is built not just on solving the problems we have, but on embracing the mysteries that make us human. The golden filaments on our cosmic map are not drawn by machines alone. They are traced by hands that tremble with excitement, by eyes strained from staring at screens, and by minds that dare to ask questions in the dark. Behind every arc of light in a gravitational lens, behind every statistical whisper of the web, there is a person. Their stories are the human heartbeat of this grand exploration. Take Dr. Chanda Prescott Weinstein, a theoretical cosmologist whose work bridges the elegance of particle physics with the vast architecture of the cosmos. For her, the dark matter map is more than data, it is a question of belonging. She speaks of how the universe, in its fundamental laws, feels like home, a place where curiosity is the ultimate compass. Her path was not a straight line from textbook to discovery, but a journey fueled by a deep desire to understand her place in the narrative of space and time. She represents a new generation of scientists bringing fresh perspectives, asking not just how the web is built, but who gets to be a cartographer. Then there are the observers, like a graduate student we will call Maya, spending long, cold nights at a remote telescope in Chile. Her world is one of meticulous routine, checking focus, monitoring weather, and guiding the immense instrument as it collects photons that have traveled for billions of years. The romantic image of an astronomer peering through an eyepiece is gone, replaced by the glow of a monitor in a control room. Her eureka, a moment is not a shout, but a quiet gasp at 3 in the morning when the software finally processes a set of images and a previously unseen gravitational arc. A faint smile from the invisible universe materializes on her screen. That single, bent line of light is the reward for months of proposal writing, technical troubleshooting, and patient waiting. It is a personal conversation with the cosmos, a secret shared between her and the dark. The challenge of working with such elusive data is a constant companion. For Dr. Alexei Luthord, an astrophysicist specializing in weak lensing, the enemy is systematic error. Is that subtle elongation in a million galaxy shapes truly the hand of dark matter? Or is it a tiny distortion from the telescope's own optics or the shimmer of Earth's atmosphere? She describes the process as detective work on a cosmic scale, eliminating every possible mundane culprit to prove the existence of a shadowy one. It requires a blend of creativity and rigorous skepticism, building new statistical tools to hear the universe's faintest signal. The pressure is immense because a single overlooked bias could skew the entire map. Yet within these massive collaborations, a powerful camaraderie emerges. Teams with hundreds of members from dozens of countries coordinate through video calls that blur time zones. They share code, debate results in shared online documents, and celebrate breakthroughs with virtual cheers. A postdoctoral researcher in Tokyo might spot a potential error in a data pipeline run by a team in Paris, saving weeks of work. This is modern science, a globally distributed mind focused on a single, profound puzzle. Veteran professors like Dr. David Spergel, who helped decode the cosmic microwave background with the WMAP satellite, now mentor these large teams. He reflects on the change from small groups to big science, emphasizing that the core motivation remains unchanged, the simple, childlike wonder of figuring out how the universe works. He finds joy in the collective stumble toward truth, in the heated debates that slowly forge consensus, and in passing the torch to students who will ask questions he never thought to pose. These personal narratives dissolve the image of the lone genius. They reveal science as a tapestry woven from late-night frustration, shared laughter over coffee, the anxiety of a conference presentation, and the collective intake of breath when a new map is unveiled. It is a human endeavor, flawed and glorious, driven by individuals who chose to spend their lives listening to the whispers of the dark. They remind us that the quest to map the invisible web is, at its heart, a very old story, the story of people looking up at the stars and deciding to draw a picture, no matter how impossible the task may seem. The journey across the invisible web is not a lecture, it is an invitation to explore. To truly grasp the scale of this hidden architecture, we need to move beyond narration and step inside the map itself. This is where the video becomes your personal observatory, transforming complex data into a direct visual experience you can navigate. Imagine the screen splitting to show a powerful revelation. On one side, the prediction from a supercomputer simulation, a delicate web of golden filaments against the void. On the other, the latest mass reconstruction from the Dark Energy Survey, a map painted with the bent light of millions of galaxies. As they fade in together, the alignment is not just close, it is breathtaking. The predicted nodes glow where the real mass clusters. The theoretical filaments trace the same paths as the gravitational shadows we have measured. This side-by-side comparison does more than explain, it validates. It shows you the moment a hypothesis graduates into a description of reality, proving that our mathematical understanding can indeed chart the unseen. To give you a sense of place within this vastness, we can embark on an animated flight. The view pulls back from our local galactic group, leaving the familiar spiral of the Milky Way behind as a shrinking jewel. We then accelerate not through star fields, but through the newly revealed substrate of the cosmos. The camera sweeps along a shimmering filament of dark matter, a river of shadow light years across, passing ghostly halos where galaxies spin like fireflies. We approach a massive cluster at a filament intersection, witnessing how thousands of galaxies are mere ornaments on an invisible mountain of mass. This fly-through, based on the latest three-dimensional reconstructions from surveys, translates petabytes of data into a visceral sense of structure. You are not being told about the cosmic web, you are traveling its hidden highways. Some concepts demand a more direct visual translation. Take weak gravitational lensing, the subtle stretching of galaxy shapes. A simple on-screen graphic can make this invisible force visible. We might see a grid representing the fabric of space-time, smooth and undisturbed. Then, as an invisible cloud of dark matter passes through, the grid lines subtly bend and warp. Over this warped grid, we see a field of background galaxies, their perfect circles gently stretched into aligned ellipses, illustrating the coherent shear that statistics reveal. Similarly, the frozen sound waves of Baryon acoustic oscillations can be shown as a ripple expanding from a point in the early universe, freezing into a preferred scale, and then being imprinted as a subtle, repeating pattern in a map of millions of galaxies. These graphics act as conceptual bridges, turning abstract principles into clear, visual metaphors, but the deepest engagement asks for your reflection. We might pause to pose a question directly to you. If you could perceive gravity as directly as you see light, what would the night sky look like? The glittering stars and nebulae would fade to background noise. In their place, the true monarchs of the cosmos would blaze forth, the immense dark halos of galaxies and the brilliant, thick knots of galaxy clusters, all connected by luminous threads of force. The familiar constellations would be gone, replaced by an architecture of breathtaking power and scale, a silent symphony of mass. This kind of prompt shifts your role from viewer to participant, asking you to internalize the wonder and the strangeness of what the science reveals. This layered approach, blending comparison, immersion, illustration, and reflection, transforms passive watching into active discovery. It respects your intelligence and curiosity, providing the tools to build your own understanding. The goal is to leave you not merely informed, but equipped with a new way of seeing, a sense that you have not just learned about the map, but have, for a moment, held it in your mind's eye and understood your place within its grand and invisible design. We have gathered the threads from across the cosmos, and when woven together, they form a single, breathtaking tapestry. This is the unified picture of the cosmic web, a complete portrait of the universe's true architecture, built from multiple, independent witnesses that all tell the same story. Each method we have explored provides a unique piece of the puzzle, and their convergence is what gives us such profound confidence in the map of the invisible. Gravitational lensing, both strong and weak, acts as our direct scale, weighing the cosmos by measuring how its mass bends the path of light. It traces the dark matter's gravitational shadow with no assumptions about what shines. The great galaxy surveys, like the Sloan Digital Sky Survey, give us the luminous tracers, the brilliant cities of stars that naturally form within the deepest gravitational wells, outlining the web's structure in points of light. The cosmic microwave background is our foundational blueprint, the fossilized imprint of the universe's infancy that tells us the total amount of matter and the initial pattern from which everything grew. And the cosmological simulations are our testing ground and time machine, letting us grow universes from those first principles to see if they evolve into a structure that matches the one we observe. When these four lines of evidence, each with its own strengths and potential weaknesses, all point to the same intricate network of filaments and halos, the case becomes overwhelming. It is the scientific equivalent of multiple eyewitnesses from different vantage points all describing the same suspect in perfect detail. The map is not a guess, it is a conclusion drawn from a chorus of cosmic data. We can now visualize this synthesis in a single, composite image that feels almost like seeing with new eyes. Picture a vast, dark field. First, overlaid in translucent hues of purple and blue, you see the subtle contours of mass density reconstructed from weak gravitational lensing, a topographic map of gravitational hills and valleys. Superimposed upon this are thousands of tiny, golden pinpricks, each one a galaxy from a redshift survey, clustering precisely along the ridges of those purple hills and threading along the faint valleys. Then, in faint wisps of red, data from X-ray observatories reveals the searing hot filaments of the warm intergalactic medium, the ordinary matter caught in the dark matter's gravitational flow. This multi-wavelength portrait reveals a full cosmic ecosystem. The dark matter shown by the lensing contours is the foundational architecture, the invisible mountain range. The galaxies are the towns and cities built on the highest peaks and along the ridges, and the faint, hot gas is the atmosphere and the rivers flowing through the valleys. Every component has its place, its role defined by gravity. This is the unified picture, a testament to human curiosity and ingenuity, proving we can chart a universe we cannot see by listening carefully to every story it tells. The stagehands of the universe have finally stepped out from behind the curtain. We have traced their silhouettes, measured their strength, and begun to understand the silent choreography that has directed the cosmic performance for billions of years. The evidence is no longer a single clue, but a converging story from a dozen different witnesses. Dark matter is not a placeholder in an equation. It is a real component of our cosmos, a vast, intricate web that forms the gravitational foundation for every galaxy we see. We have learned to read its signature in the bent paths of ancient light, to hear its echo in the first heat of creation, and to reconstruct its architecture in the clustering of a billion stars. This map of the invisible is one of humanity's greatest intellectual triumphs, a testament to our refusal to accept that what we see is all there is. As leading cosmologist Dr. David Spergel once reflected, the universe is kind enough to give us puzzles, and it's kind enough to give us ways to solve them, but it never makes it easy. This journey has required humility, patience, and a profound sense of awe. So the next time you stand under a clear night sky, let your perception shift. See beyond the glittering points of light. Envision the immense, silent filaments stretching between them, the vast halos cradling each spiral and ellipse, the hidden architecture that makes the luminous universe possible. This is the true cosmos, a grand theater where most of the actors are made of shadow. Our exploration is far from over, of course. The nature of the dark matter particle remains the next great mystery, and new telescopes will soon deliver maps of unprecedented detail. If you found this journey into the shadows compelling, consider subscribing for more deep dives into the universe's greatest puzzles. We would love to hear what captivates you most. Share in the comments whether it is the ghostly evidence of gravitational lensing, the simulated universes born in supercomputers, or the profound philosophical questions this hidden reality raises. Thank you for exploring the invisible web with us. Keep looking up and wondering.